Okay, hi guys. This video is about aldehyde, ketones, and carboxylic acid. I'm going to discuss the tutorial questions. So let's first look at the learning outcomes, right? So first things, we must be able to recognize and name carbonyl compounds according to IUPAC system, and able to describe the formations of carbonyl compounds from alcohol, like how we can get carbonyls compound like aldehyde and ketones, which I've shown you in class. And the third one is to able to describe the reductions of carbonyl compounds using common reducing agent, like what? LiAlH4 or NaBH4. Right? So just remember that LiAlH4 is supposed to be in dry ether, NaBH4 is supposed to in alcohol or even aqueous. All right. For number 4, able to describe the mechanism of nucleophilic additions of hydrogen cyanide, the HCN. This is the only nucleophilic additions reactions for aldehyde and ketones using HCN. Okay. Next one is the test for aldehyde and ketones like 2,4-DNPH, Tollens reagent, Fehling solutions, as well as iodoform tests. So the last learning outcomes will be able to describe the formation of carboxylic acid from alcohol, aldehyde, and nitriles. So knowing that alcohol, primary alcohol, especially when you oxidize it, you will get aldehydes, then further oxidize into carboxylic acid, right? And for aldehydes, you may just oxidize it further a little bit more, then you get carboxylic acid. And for nitriles, is a compounds that compose of CN, cyanide, CN, right? C triple bond N. Again, when you use acid or base aqueous solutions, hydrolyze them, heat reflux. So either we call it as acidic hydrolysis or alkaline hydrolysis, you will turn the CN into COOH. So these are the learning outcomes that we need to know about this topic. And let's look at the first questions. So study the organic reactions below. Sorry, it's a bit blur, the image, when I copy it to the PowerPoint. So let's look at the first one. Okay, we shall focus on this, the C2H5Br, all right, the C2H5Br going through reaction number 1. So basically, you're changing the C2H5Br into an OH, right? If you look at the structural formula for both compounds, the only difference is the OH substituted the Br. So in this case, what reagent and conditions will we suggest? So I'm going to suggest NaOH aqueous. This is nucleophilic substitution, SN2 reactions, because obviously 2 carbon, it is just a primary structure. All right. And in terms of conditions, of course, we need to heat reflux for most organic reactions. So that's the first one. And the next one, we're going to get CH2 with a double bonds. So in this case, if we check the structural formula again, the only things that we remove from the molecules will be HBr, so that we can get the double bonds there. So in this case, we call that as elimination. So again, we are using similar reagents, NaOH, but then this is in alcohol, ethanol. All right, and because of ethanol involved, because of organic compounds involved, again, we have to heat reflux. All right, that's for second. And for the third reactions, C2H5Br, it turned into C2H5CN. So Br is being substituted by Cn. Cn itself is minus with lone pairs. Carbon, 1 lone pairs, nitrogen, 1 lone pairs. So this is how it looks like. C triple bond N with 1 lone pair here, 1 lone pair here, and overall is a negative charge ion. So this obviously is a nucleophile, and we can see that it substitutes the Br. Again, this is under SN2 reaction, nucleophilic substitutions, and what reagent and conditions that we're supposed to use here will be KCN, any methyl cyanide, KCN or NaCN, and then in ethanol as well, or sometimes we call that as ethanolic KCN, right? And you have to heat reflux, of course, as usual. And then for number 4, right? So you're changing the CN into COOH. See, that's to remember during the learning outcomes that I've gone through with you. CN turned into COOH is either acidic hydrolysis or alkaline hydrolysis. So the reagent is just simple. You just need to add any acid like HCl, HNO3, H2SO4, but make sure it is diluted form, right? Aqueous. So when you put aqueous here, basically dilutions. Otherwise, you have to put concentrated. Again, if you put aqueous, it's well known as it's well known as a diluted solution. So you just need to heat reflux with any acid, all right, any strong acid, then you can turn the CN into COOH, then you turn it into carboxylic acid. Okay, number 5. So number 5, obviously, I'm changing a carboxylic acid. Let's name this. This is propanoic acid. right? 3 carbons. And this propanol acid is turning into this for reaction number 5. C2H5COO, the H converted into CH3. Now, obviously, this is COOC. COOC, that is an ester, right? How to convert a carboxylic acid into an ester? You react with the alcohol, right? So in this case, the alcohol should be like that. Now, how can we identify an alcohol? Let me show you again. I've shown you in class, but then let me show you again here. Just a reminder, it should be like that. The COO, you're going to split them apart. The 2 oxygen, you split them apart. The first one with the CO is actually C2H5CO on the left is actually the carboxylate group, the carboxylic acid. And then the remaining part on the right, CH3O, is actually the alcohol. So obviously in this case, we are reacting it with CH3OH, a methanol. And then of course you will need concentrated sulfuric acid as a catalyst, heat reflux for esterification. Okay, that's reaction number 5. And reaction number 6 then. So in this case, again, changing from carboxylic acid, propanol acid into this. So what is that? So C2H5COO still the same. Again, it's just because of the H replaced by ammonium. So this is a neutralization reactions. Let me show you the equations. So it's actually C2H5COOH. This is an acid plus ammonia, which is a base. What happened is acid is a proton donor. This is a proton acceptor, right? So what happened is this proton is going to be donated to this, forming NH4 plus ions. And this proton donor will turn into C2H5COO negative. And because they have oppositely charged, negative and positive, they attract to each other, you get a salt. So the name of this salt, we call that as ammonium, because NH4, ammonium propanoate. Just like if you're reacting with NaOH, you are getting sodium propanoate, right? That's a salt. But in this case, instead of sodium, we are using ammonium. That's also a salt because, yeah, you know, ionic interactions, ionic charge. This is an ionic compound in a way, so that's why it's a salt. So ammonium propanoate. This is for reaction number 6. Now, reaction number 7, we will ignore it because this is not a I realize this is not a proper compound. This is not a chemical compound because it doesn't make sense to have C2H5HO. The best is C2H5OH, which is the same as this one. So no point actually referring to this. You can ignore that. And we are not learning any reductions reactions here about carboxylic acid. So therefore, number 7 can be ignored. So in this case, we have listed out all the 6 reactions together with the conditions and reagents. So this is what they want for question number 1. Okay, let's move on to question 2. Okay, primary and secondary alcohol can be oxidized by heating with a mixture of potassium dichromate and dilute sulfuric acid. Okay, now for oxidations, we need common oxidizing agent, which is either potassium dichromate in this case, K2Cr2O7, acidified. See that in this case, they don't put acidified, but just that they put potassium dichromate and dilute sulfuric acid. That means acidified. All right, so either you put /H plus like what I did, or you put dilute sulfuric acid as part of the mixture. So in this case, potassium dichromate is actually one of the common oxidizing agent. Another one will be potassium permanganate, KMnO4, but then both are comparable. You can use any one of them, but make sure that you acidify the mixture. Now let's look at the first one. A primary alcohol can be oxidized to 2 different products depending on the condition used. Yes, apparently, because primary alcohol can be oxidized into aldehyde only if it is still off the product, or you can actually produce carboxylic acid if you heat reflux without distilling it off, like prolonged heating. You will get eventually a product which is carboxylic acid. Then secondary alcohol in this case will form only one product, and that referred to ketones because ketone cannot be further oxidized. Tertiary alcohol cannot be oxidized. That's the reason. So these are a short theory or reminder. So let's look at A. What is the formula of potassium dichromate, which I've written it down here, K2Cr2O7. You don't have to /H plus because they just asked for the formula potassium dichromate. All right. So let's look at part B then. Using a primary alcohol of your choice as an example, give a display formula of the 2 product it could be oxidized to. Let's work it out one by one. Now, for part one, you have to use your choice of primary alcohol. In this case, I'm going to use ethanol. Okay, so C2H5OH. So this is actually the formula of ethanol, and if you actually oxidize it, okay, by the way, this is primary alcohol. So when you first oxidize it, you're actually getting, again, guys, this square bracket O is to indicate oxidation, which can be used in the equation I'll show you in a while. So when you oxidize primary alcohol, what you need to remove is that we were going to remove the one hydrogen from the O, right, from the OH, and one more hydrogen from the adjacent carbon. So basically, you're getting CH3, CH double bond O. All right. Okay. Just to avoid confusion here, I'm going to draw this ethanol in a proper structural form, which means I show you the carbons CH2, CH3, CH2, OH. Okay, so what I meant was I remove the, sorry, I'm changing the color. I remove the H and then remove another H from the same alpha carbon here, which is here. So you left one hydrogen, CH double bond O. See that? So you get an aldehyde. Now this one is by distill off the products, right? You will get this. And then you can actually further oxidize this aldehydes by prolonged heating. And what you're going to do is you will get CH3, C double bond O as usual, but the only H just now will turn into an OH by additional one oxygen. So you get an ethanoic acid then. Okay, so let me give you the conditions for each product. For the first one, you have the heat reflux as usual, but then you distill off the product immediately. So from here to here, you distill off the product. Okay, distill off the product if you want aldehydes alone. But if you want carboxylic acid, then you don't need to distill off, you just need to heat reflux all the way until you get the carboxylic acid. All right, and state which homologous series each product belongs to. Aldehyde belongs to carbonyl compound, carboxylic acid, ethanoic acid belongs to carboxylic acid then. All right, now I want you to pay attention to this part 4. Write a balanced chemical equations for each reactions. The conversions of oxygen may be used as oxidizing agent. So this is what I meant just now, the square bracket O. Okay, so I'm going to show the equations here one by one for each reactions. First, I'm going to show you how ethanol changes into, by adding oxygen, you change it into an aldehyde, CH3, CH double bond O, right? That's first reactions. Now, in this case, obviously, I'm removing two hydrogen, like I did just now. So in this case, by adding one O in the balanced equations, I'm adding H2O. See that? The H from here and one more H from here together with the O from oxidizing agent, you're getting a water. So this is the balance equation for the first part. And if you want to get a carboxylic acid, right? If you want to get a carboxylic acid, basically you need to extend it further. So I'm going to show you all the way. So CH3, CH2OH plus 1O, removing two hydrogen, and you're getting CH3, CH double bond O, right? So you're getting this. And what next is you're going to add another O because it's further oxidations. And then you will going to get CH3, C double bond O with OH. All right, so you're getting a carboxylic acid. So of course, byproduct would be, in this case, you're adding H2O on this side. And next one is the COH, you're adding one O into it only, right? So no other byproducts here. This O is being added to the H here, hence you get the final carboxylic acid. So this is the full equations where we get a full balance equations where we get the different products for oxidations of primary alcohol. Get that? So let's move on to the next part where we have, let me erase everything. Oops, sorry. Okay, the next part is by using a secondary alcohol of your choice. We know that we're going to get ketones, so this is less complicated. Let's start with a secondary alcohol. So I'm going to start with COH with a CH3, CH3, and a H, right? So what is the name of this? This is propane 2-ol, okay? Propane 2-ol. So this propane-2O is going through an oxidations. What you get is, again, I'm removing the H from the OH, I'm removing the H from the same alpha carbon here, therefore the bond move up, you will get C double bond O with 2 CH3 attached. So this is actually a ketones. Or the real name, I mean the IUPAC name for it is actually propanone. Okay, so that's propanone. And can we further oxidize it? No way, we can't do that. So that's it. This is what happened. And next, they want you to show the balance equation of, oh yeah, before that, homologous series, obviously same as aldehyde under carbonyl compound. So in this case, write the balance equation. I guess it will be less hassle, less complicated. So you have CH3, because I have two CH3 attached to the same carbon, I can write it as this way, in such a way, bracket 2, and then CHOH. You can do in such a way if you want, okay, and then plus with square bracket O, all right, and then you know we're going to remove two hydrogens, right, minus two hydrogen, and then you will get the resulting ketones, CH3, C double bond O, CH3, plus what? You have oxygen, you have two hydrogens, so there you go, you get H2O. So this is the balance equations that they want for part 3. And the last part will be why a tertiary alcohol resistance to oxidations, right? Why is it resistant to oxidations? I guess I explained that in class. Why is it resistant to oxidation? Because we know that in the first stage of oxidations of an alcohol, we always remove two hydrogens. And looking at the structure of a tertiary alcohol, I guess I can erase all this. So a tertiary alcohol is like attaching to 3 R group. So the simplest R group is CH3, of course, in this case. So then if you are trying to remove 2 hydrogen from it for the first oxidation, H from here, alpha carbon, we are supposed to remove another hydrogen from the alpha carbon, and sad to say that we don't have any. In this case, the carbon is attached to 3 R groups, therefore no other hydrogen is available, therefore it can't be oxidized. Okay, you can explain in such a way why is it resistant to oxidations. Okay, move on to question 3. Now question 3 is just naming and drawing of the structure. So name the following compounds. I'll go through quickly and just count the number of carbons. We have 1, 2, 3, 4, 5, 6. So it's hexane, right? Hexanal. Al, aldehydes. So in this case, obviously it's a ketones, and we have 1, 2, 3, 4, 5, 6, 7, 8. So it's octanone. Okay, octanone. Okay, or you can write it as octane 2-on. Why? Because the carbon C double bond O is carbon number 2 here. So either way would do, but of course if we move in between, like move to the carbon number 3, number 4, then it's good to put in the numbers so that people would know, whoever reading this, they would know the position of the C double bond O. You see that? Right? So draw display formula for each of the following methanol. It's just simple. Of course, display formula is not what I show you here. Display formula is supposed to be the one that open up the structure. So CH3OH, that's for the first one. All right. For propanol, it's actually CH3, 3 carbons, right? It's an aldehyde. So 2 carbons. The last carbon has to be C double bond O with H. So this is propanol. Okay, open structure. And the last one will be pentane 3-on. So it's a pentanone, 5 carbons, and the C double bond O, like in this case, is at position number 3. So same thing, I've drawn 5 carbons. You may do in such a way. And then third carbon is double bond O, and the rest you just put in hydrogen. Make sure each carbon is forming 4 bonds. That will do, right? So that's how it looks like. And look at number 4. Okay, 4A. Write a balance equation for the oxidations of ethanol to, this is actually ethanol, using the O to represent an oxygen from oxidizing agent, which we have done it in question 2, so I'm going to skip this. Part B, refer to questions 2, right? So give practical details. Explain how you would use the reaction described in part A to prepare and collect a sample of ethanol. So what practical details? You have to mix ethanol and ethanol together, okay? Mixing ethanol and why am I adding ethanol? ethanol and KMNO4 acidified together equal molar. Equal molar meaning that same concentrations. You put them in the same mole ratio, right? 1 to 1. So ethanol plus oxidizing agent, and then what happened? You have to heat reflux them, reflux it, and then don't forget, because you are getting ethanol, right? So then what do you do? Distill of the product form. So once the product form, the first one would be aldehyde, ethanol, then you distill it off so that you won't get any carboxylic acid. So that's the answer for B. Okay, just some small little details for the practical part. Okay, let's move on to part C. Write balance equation for butanol into butanone. Now, it's slightly different from what we did just now. Let me show you butanone, butane 2-ol. So butane 2-ol is 4 carbons, and 2-ol means you have OH at carbon number 2. The rest are all hydrogen, right? So in this case, we're going to oxidize it as usual. You will get a ketones, right? So we shall remove the hydrogen here and the same hydrogen from the alpha carbon. Therefore, these bonds will move in to form double bonds, and you draw the same thing as just now, just that this turned into carbon double bond O, and the rest the same, right? And I remove 2 hydrogen together with 1 O, so plus H2O. So this is the balance equation they're looking for by putting this. Again, guys, this is like a square bracket symbol. Yeah, because the conversions from words to PDF sometimes and using different devices, it tends to show like a usual bracket, but no, it should be a square bracket. All right. So for part D then, what do you observe in the reaction vessels if the oxidizing agent used in part C is potassium dichromate and acidified dilute sulfuric acid, and the reaction mixture is heated? So basically, they're asking for the color change. Now, just now from the first part, which I'm showing you the practical details, part B, right? I'm using KMNO4. That will be from purple to colorless, but then for D, it's supposed to change from orange to green if you're using potassium dichromate. And that's the observations that asking for. Okay, so orange to green, guys. Okay, let's move on to number 5. Write a balance equation for the reaction that takes place when propanol is warmed with sodium tetrahydroborate. Now, this sodium tetrahydroborate is actually NaBH4. Okay, that's a common reducing agent using the symbol H. Again, this is supposed to be a square bracket to represent a hydrogen atoms from the reducing agent, knowing that reducing agent is going to provide hydrogen atoms so that the compounds can get reduced, right? So they want a balance equation for part A. It's very simple. Propanol is 1, 2, 3, double bond O with H, right? And the rest all H. So in this case, we're going to reduce it. So let me show you the reduction mechanism instead of just a balance equations. So what's the mechanism here? Now, in this case, NaBH4 is going to provide H minus lone pair. This is what we got from the reducing agent NaBH4, which can be represented by square bracket H. Okay. Now, this lone pair from the H minus, which is the hydrides, is going to attack the delta positive carbon here. And then the pi bonds here, double bond will break. And then you move on to the next step where we have C single bond O. Now you have extra lone pair here because the pi bond break. And then you have your H attached to it. See that? And then the rest remain the same. I'm not drawing the rest of the hydrogens, just that I don't want to confuse you. So in this case, you have O minus, right? And this O minus, you still have a lot of NaBH4, Na plus, BH4 negative. You still have a lot of hydrogen here. So the lone pair from the O minus is going to grab any hydrogen from the BH4, and then you will get your final structure as OH here, H here, and the rest remain the same. Now let me highlight that. So the overall reaction is by adding 2 hydrogen into it. So one is to the OH, one is to the O, one is to the same alpha carbon. See that? Right? Which is exactly the opposite of oxidation. Still remember? Oxidation of an alcohol is removing 2 hydrogen. Now, if you want to reduce an aldehyde or a ketones back into an alcohol, Of course, we need to put back the two hydrogens at the same place where we remove it just now during the oxidation. So this is how it looks like, and you will get a secondary alcohol. So this is the secondary alcohol that they want. So this is in terms of mechanism with the curly arrow number 1, curly arrow number 2, curly arrow number 3, right? So in terms of balance equation, which I'm going to show you now, how would it look like is like that. So you have CH3, CH2, CHO. This is how I write an aldehyde, propanol, or you may write C double bond OH, up to you. I'm going to write add with H. Remember, this is actually the H, the two hydrogen that we're going to add in. So you're going to get the alcohol instead. Okay, so you're going to get an alcohol. So CH2 and CH, supposed to be O double bond, but now it's OH and a H. Again, these two hydrogen is additional from this. Therefore, to balance it, we have to put 2 here, and that's how you get that. So this is the balance equation for part A. This represents reducing agent. Okay, and now we look at B. Name the product form in the reductions of reactions if pentane 3-on is warmed with sodium tetrahydrodoberate. Again, reducing agent. This is a propanone, ketones, pentanone, right? Pentane 3-on, when you reduce it, what would you get? You ask yourself, how would I get a pentane 3-on? A pentanol, right? A pentane 3-ol. A pentanol with OH at carbon number 3, then you get a pentane 3-on by oxidation. Now, if you reduce it back, you will get pentane. It's an alcohol now, same place, carbon number 3, pentane 3-ol. So this is the name for part B. All right, balance equation and name. So number 6, name the organic product that will be formed in the nucleophilic additions of HCN on ethanol. So I'm going to show you either one of them. Okay, I guess I show you ethanol or aldehydes in the class. I'm going to show you propanol now. So it's CH3, C double bond O with CH3. In terms of balance equation, I'm going to add HCN as a reagent, KCN as a catalyst. Again, K plus Cn minus is an ionic compound, and then you will get CH3C, the O become OH. Here is the Cn, and here will be the CH3. Now, just highlight this. I've added the H and the Cn into the structure. That's why they call it as addition, and it's due to the nucleophile. I'm going to show you that. Okay, so catalyst remain unchanged, HCN has been added into it. So what happened to the mechanism? So the mechanism should look like this. CH3, C double bond O with CH3 again. And remember, the nucleophile is actually from the catalyst, Cn minus, lone pairs. Again, the C lone pairs attack this, delta positive, delta negative, bond breaks. So more or less the same as reduction like just now. C O negative lone pairs, Cn attached already to it after the attack. So now you have to get rid of this lone pairs and the negative charge. So what happened now? The HCN comes in. This is the reagent, right? So only comes in the step 2. So what happened? Delta positive, delta negative is a covalent molecules with dipoles. So now what happened is the oxygen with the lone pair attack the hydrogen. The HCN bond will break. All right. Then only you will get the final compounds or the product as COH with Cn and CH3 plus Cn negative lone pairs. See that? This bond break and get back this here. Okay, so you're generating the Cn minus. I use up one, I regenerate it, so which means I don't use that anymore. I return it back. So that is the purpose, or that is the function of a catalyst. So this is the full mechanism for nucleophilic additions of HCN. And don't forget, this reaction gotta be happen or take place at 10 to 20 degrees Celsius, not any higher than that. All right, this is cold. So don't simply put in heat under reflux. That will not make sense. Okay, so yeah, I have done the mechanism for this. It's the same thing basically. If you want to do the ethanol, you just change the propanol, this structure, into ethanol. Everything follow the same, even though the curly arrow remain the same. Okay, number 7. So the melting point of the derivative of the reactions between 2,4-DMPH and various aldehyde ketones are shown in the table, and we have all this. See that? So what will be observed when each of the carbonyl compounds in the table is mixed with 2,4-DMPH? Let me remind you here, 2,4-DMPH is a compound that will give us yellow precipitate or orange precipitate if it reacts with either aldehyde ketones. I mean, it can show precipitate with both. Whatever carbonyl compound, put it that way, you put it in tight with 2,4-DMPH, you're expecting yellow or orange precipitate. So that's how we observe. So what we observe, yellow and orange precipitate. So that's for A. For B, a derivative was formed between 2,4-DMPH and an unknown carbonyl compounds, right? So the melting point of the derivative was 126 degrees Celsius. What does this result tell you? Okay, now what does that mean? A derivative was formed when between 2,4-DMPH and unknown carbonyl compound. Basically, this derivative is referring to the compound responsible for the yellow and orange precipitate. Make sense? So this is actually the compound form that combined with the 2,4-DMPH, right, to get the orange and yellow precipitate. So the melting point of this precipitate is actually 126. What does it tell you here? Now, if you combine with 2,4-DMPH, in this case, getting a yellow precipitate, the melting point of this derivative is telling you the identity of the carbonyl compound that mixed with it. The melting points remain almost the same. That's a good point. That's a good thing about it. So we can tell by measuring the final product, the melting point, we can tell what carbonyl compound, aldehyde or ketones, what aldehyde and what ketones actually combine with the 2,4-DMPH to form this yellow precipitate. So in this case, 126, referring to the table, we can tell it's either butanol or propanol because both are having the same melting point. Done. Okay, either butanol or propanol. That's what we can tell for now. Part 2, the unknown carbonyl compound, either butanol or propanol, not sure which one, that's why they put unknown, form orange precipitate when warmed with Phalling solution. Now, this Phalling solution is a task mainly only for aldehydes, like Tollens reagent as well. So please remember that Tollens and Phalling solutions both are meant for only aldehydes. No reactions, no positive results with ketones. So in this case, they get an orange precipitate, supposed to be red, with Phalling solution. What does it tell you? The unknown compound should be butanol, not the propanol. So from the second step, additional test we can tell is butanol. All right. And for the last part, describe and explain the different results obtained when compound name in part B2 it's warmed with Tollens reagent. Right. So again, Tollens reagent is giving us silver mirror or silver solid or silver precipitate because the formation of silver metal, right? So if it is an aldehyde, so what will happen when you mix with Tollens reagent? Because it's butanol, so it will give us the silver mirror. This is what we observe. And explain the result. No need to explain. Because it's aldehyde, it reacts with Tollens reagent to give us silver mirror. That's about it. That's what needed. Enough, right? Okay, part C. Write half equation to show silver ion acting as an oxidizing agent in a positive test for aldehydes. Okay, now what's going on here? In this case, Tollens reagents is actually a mixture of silver ions. Is a diamine silver ion. This is the structure of Tollens reagent, and initially the charge of silver is actually positive. And what happened at the end? It turns into solid, 0. So charge here is positive and turned it 0, ion to solid. So how they act as an oxidizing agent? Because it get reduced. So the equation they want here is just simple as that. Ag plus E, you're getting Ag solid. That's a reduction, right? Therefore, this is an oxidizing agent. Okay, so this is what they want for C. And for next one, part D, let me erase that. For D, write a half equation to show copper 2 ion acting as oxidizing agent in a positive type for aldehyde. Now, copper ion is actually in the Phalling solutions. In the Phalling solution, it is actually changing from copper 2 plus into copper plus ions. And this copper plus is going to mix with the oxide from the solution. They're changing into copper 2 oxide like that. You see, O2 minus Cu plus. So this is actually a precipitate, which is the observation, the red or orange precipitate. This is what we got from Fowling solutions when you react with an aldehyde. All right, so they want a half equation. So as simple as copper 2 plus E, you're getting copper solid. Copper plus aqueous. And this copper plus then only turn into this by reacting with the oxide. So what they want is just these half equations. Electrons, 1 electrons, right? And then you get a copper plus. So it's a reduction here. Therefore, this is an oxidizing agent. So an oxidizing agent will always undergo reduction by itself. So this is the answer for D. Okay, number 8. Ethanol can be made from ethanol using sodium tetrahydrodoberate, NaBH4, as a reducing agent. So I've shown you this before, but I'm going to show you again. First one, give the formula of this NaBH4. What other reagent is necessary for the reaction to take place? Like I said, NaBH4 is either in alcohol or aqueous, commonly alcohol. So what other reagent needed for this reaction? You just need to put in alcohol, any alcohol, commonly ethanol. All right, part A and B done. Part C, basically the mechanism for these reductions, right? They explain a lot of things here, which you can actually ignore it. They're trying to brief you. They're trying to guide you how to write the mechanism. So the mechanism, again, I'm going to show you once again. The mechanism for the reductions will be ethanol, CH3, CH2OH. Oops, we're forming ethanol, right? My gosh, what am I doing? So in this case, we're supposed to start with ethanol because we are going to get ethanol at the end. So ethanol is actually with this formula CH3 C double bond O with H. Again, this NaBH4 is going to provide us with a H minus lone pair. Basically, it's a hydrogen provider. It can be positive, it can be negative. In this case, of course, the H minus is the nucleophile attacking the delta positive carbon, like break the bonds, and then you get CH3, C single bond O negative lone pairs. You get a H added into it, right? And then again, this thing is going to attack. Now, because it's in ethanol or in NH4, you can actually do that. I just standardize it, BH4 minus. So this thing, the lone pair here, attack one of the H from it, and then you will get CH3, COH, H, and H. You get ethanol. All right, curly arrow number 1, curly arrow number 2, curly arrow number 3. So that's how it works. So this is for the part C, the mechanism for reductions. It's the same as nucleophilic additions. Okay, number 9. Croton aldehydes occurs in soybean oil. So in the box below, write the structural formula of the organic compound form, if any. If no, then you just write no reaction. So let's see what's happening here. Now, first thing first, from this compound, what we can see here is I have a double bond and I have an aldehyde. So these are the things you need to identify prior to any reactions. So in this case, the compound having two functional groups, aldehydes and alkenes, right? Two functional groups here. So we have to check each of this reagent added, which one they can react with, either react with the aldehydes or react with double bonds or even both sometimes, right? So in this case, what will be happening here? Bromine in organic solvent. So bromine in inorganic solvent basically reacting with double bonds, I guess. So in this case, you will get CH3, CH, no more double bond, single bond, CH, CHO, aldehyde remain the same, no changes. You have two Br added in. So this is under electrophilic addition. All right. And for PCl3, what is that for? PCl3 is basically a reagent changing OH into Cl, nucleophilic substitution, but we are changing any OH into a halogen, PCl3. In this case, do we have alcohol? Do we have carboxylic acid? Or do we have OH group? No, we don't. So therefore, no reactions. Okay, so for the C, hydrogen and nickel, again, you're adding hydrogen under the same reaction, electrophilic addition here by adding hydrogen. Okay, but then, right, hydrogen plus nickel is also considered as a strong reducing agent. So not only breaking the double bonds, like what I show you here, CH3, CH single bond, CH, you're adding 2 hydrogen onto it. You're not breaking that only, but also reduce the aldehyde. So aldehyde is going to be reduced into C double bond OH. This is the original aldehydes, right? What you're going to get is you're going to get C, no more double bond, single bond with a H and add another H here, reductions. So you will get an alcohol at the end and also added 2 hydrogen into it. So you are reacting with both in this case for reagent C because it's a reducing agent and it also electrophile, all right, for hydrogen gas. So that is for part C. And for part D, reducing agent. Now, what's the difference here? I want you to pay attention into this C and D, right? So the only difference between them is that hydrogen and nickel is a strong reducing agent which can be used to reduce aldehyde into alcohol, like what I did just now, as well as changing a double bond into a single bond by adding 2 hydrogen into it. But for NaBH4, the commonly used reducing agent, this is much weaker. It's a mild reducing agent. So what happened to a mild reducing agent use? So the only difference is that you will change the aldehydes again into the alcohol. You actually can reduce it into an alcohol, like what I did all the while. So you're changing the aldehyde into alcohol, but then you see that the double bond remains there. This NaBH4 is not a strong, it's not an electrophile. So they can't actually do electrophilic addition, breaking the double bonds and put in the hydrogen because, like I said, NaBH4 is providing H minus mainly. So therefore, the double bond will still be there, only the aldehyde changed. So please pay attention to that. NaBH4 only reduce aldehyde and ketones, but not double bonds. If you want to reduce both, then hydrogen nickel got to be added. All right. So for E, oxidizing agent, obviously, and acidified. But which one can be oxidized? In this case, you can oxidize the aldehydes only. You can't oxidize the double bond. Why? Because if you want to break the double bond and split them apart, like I showed you last week, you need to use KMNO4 only. Right? You can't use dichromate to do the case. So in this case, CH3, CH, double bond, CH, and then the CHO, the aldehyde will further oxidize into what? COOH then. So you get a carboxylic acid, double bonds remains there unless you change the dichromate into KMNO4. Then yes, you split them apart. Otherwise, that's only reactions. Okay, let's look at the last part. Now, in a school or college laboratory, it is possible to convert a sample of hydroxy ethanol into aminoethanoic acid. Now, regardless of how they name it, how fancy the name is, doesn't matter. You just need to check the compound, the formula, and what's the changes, as well as the functional group present. That's the things you need to do when you analyze chemical reactions. Now, in this case, obviously, I have aldehydes, CHO, and CH2OH, a primary alcohol. Don't just say alcohol is a primary alcohol because different alcohol, primary, secondary, tertiary, may give a different chemical properties, right? So in this case, I have aldehyde and alcohol. At the end, I'm changing into a carboxylic acid. Right. And then I'm changing the OH into the NH2. So what's in your mind is that we are trying to think how to change this thing to do the conversions like what it is in 3 steps, right? And the sequence of changing it makes a difference though. So in this case, what we're going to do here is we shall change the OH into halogenal alkane. So in step 1, I'm adding PCl5. So what happened here is your X is actually when you add PCl5, right? You are replacing the OH into Cl. and then aldehyde remain the same. Make sure the PCl5 added, whatever added, no change to the aldehyde at first. We change it one at a time. So you'll get this as X. You have a Cl instead of OH. Now, how do I change the Cl now into NH2, which what we want at the end? Nucleophilic substitutions. So what we're supposed to be added? Step 2. If you remember, we just add concentrated ammonia, which we will get NH2 at the end, right? So this is nucleophilic substitution. The lone pair from NH3 attack the carbon here, and then you replace the Cl. And the final structure is CH2, NH2, like what we want, and the CHO, the aldehyde, still the same for Y. We don't change it yet. Then only in step 3, we're going to change this into a carboxylic acid. How to change an aldehyde into carboxylic acid? As simple as adding KMnO4, oxidations, acidified. There you go. So you change it into this compound then. So this is how we change it step by step into the final compounds that they want. So you're expecting this in your exam. All right. So next, we're done with this step 1, 2, 3. Let me know in class if you need any further help. Part 1, in the box below, you have drawn the, I've shown you. So let's look at the last one. State the reagent for each of the 3 steps you have chosen, which I've done it as well, right? So PCl5, concentrated ammonia, and KMnO4 oxidizing agent. That's about it. So that's it for this tutorial, aldehyde, ketones, and carboxylic acid, right? So yeah, thank you for watching. I'll see you again in class.